Okay, go ahead.
Everybody,
Good morning.
welcome to our 2019 dress rehearsal for the Cleveland section American Chemical Society's 2019 National Chemistry Week celebration. During this dress rehearsal, we'll be going through a lot of the experiments that we have put together for the year. I'd like to begin by acknowledging the members of our planning committee who are here, starting with our newest member, Susan Wang, who's come to us from the Case Western Reserve University. Helen Mayer, Shavona Singham, Mike's over here. Mark Weiner over here, Vince Oposhker, Lois Kuhn, say hello, Lois. And Lois let me know a little while ago, this is our 25th anniversary for actually doing the National Chemistry Week program in libraries, okay? Turns out that we always use the theme that the National ACS gives us, and this year the theme is Marvelous Metals. I'm Bob Fowler, by the way. Did I introduce myself? This year the theme is Marvelous Metals, and what we're going to be doing is we're going to be showing the uses and the properties of marvelous metals as we go through the 6 experiments that we had. Couple of housekeeping things before we get started. First of all, something that all the demonstrators, you people out there in TV land or whatever, computer land would like to know, there's always a feedback form for the demonstrators to give us their comments on this year's program. But on the back of this year's form, there is a cheat sheet. A cheat sheet that you can refer to as you go through your demonstrations at the various libraries or wherever you're presenting the program. So that's on the back of the demonstrator feedback form. Another item you probably want to be aware of is the Errata Sheet. On page 3 of the script, we give you the local section's new website address. And on the website is a copy of the script, by the way, a corrected copy of the script, as well as this Errata Sheet. Now the Errata Sheet really only pertains to the hard copies of the script that are in the kit boxes. It's kind of hard to change a hard copy once they've been done. So this Errata Sheet applies to the hard copy script sheets. Lastly, on the back of one of the other forms, I believe it might be this form. Yes, it is. Actually, there's 2 copies here that all the kids are getting. One is not a crossword puzzle, but a word puzzle that we're going to complete as we go through the experiments today. And there'll be a magic word that pops up. You'll never guess what it might be. There'll be a magic word that will pop up as we go through the experiments. And on the back of that same sheet is a sheet with 3 different items on it. Number 1, we're going to record the results of experiment 4, part 2 at the top part of this thing. In the middle part, it talks about how to put together a compass on your own at home, and down at the very bottom, it gives you instructions for how to perform experiment number 6 with memory metal wire in case we don't get there. So those 3 things are on the back. Last thing in the way, one other item of housekeeping to pick up on is the fact that each one of the students has this little package at their place. It has a cork in it, it has a National Chemistry Week business card, quote unquote, and it has a blank magnet. On the back of that sheet I referred to a second ago, are the instructions for putting together a card magnet that can be used on the refrigerator like the other thousands of card magnets that are on people's refrigerators. And there's also instructions on how to make a cork pointer like a compass. We did not include a nail. It says so in that, on the back of that sheet. Specifically, we didn't want kids to be poking their eyes out with nails. So it says on the back of the sheet, with reference to this cork, that if the kids want to take this home, and that's what it's for, take it home. If they want to take that cork home and make a compass pointer at home, it has to be under the supervision of an adult, which hopefully the adults will watch over the kids as they use a finishing nail to make that compass pointer.
Big corks I might add.
Pardon me?
Already pre-drilled.
The corks are already pre-drilled, so all they have to do is put the nail through the cork.
No,
And
they're not. These are not.
they're not?
No,
These are, maybe those are, and
Look hard.
Nope.
It should be through the side. I don't believe they are, Vince.
No, they're not.
But a nail goes perpendicular through the cork to make the thing. Yeah, and we'll show examples of that. We have some already pre-made. Okay, with all that having been said, I'd like to introduce Susan Wang, who's going to start us off with demonstrating experiment number 1. Take it away, Susan.
Hi, sorry I'm fogging up a little bit under my goggles. So for experiment 1, I don't know if I need to go through all 7 of the items, but it's pretty simple. The one thing to note is that we discovered in setting up for this dress rehearsal today that items number 1 and 2 that are supposed to be 40 mils each of copper sulfate, cobalt sulfate, excuse me, is number 1, and copper sulfate is number 2, only have 10 mils each in them, but that shouldn't matter in terms of the big picture of things. There's also a vial containing water, that's 10 mils. There is a tiny vial of sodium borohydride, that's marked S. It's the only solid in this experiment. We've got 3 little cups that are marked, and then a stirrer and one of these barrel or dropper pipettes. So as far as illustrating this, experiment one more handy than this. So what you're going to do is go ahead and open these containers that are paraffin shut to avoid drippage. And of course make sure that you have goggles on.
Let me help you with those, Susan. Sometimes just opening them will do the trick and remove the paraffin.
And you're going to transfer solutions 11 into the cup marked 11 and 12 into the cup marked 12.
not just this, just demonstration.
And yeah, and in case that wasn't clear, this is a demo. You are going to do this. The students are not going to do it. So you only have one of these per demonstration kit. So this part is kind of important, which is the water gets added to the sodium borohydride. Those of you that do this type of chemistry will know what ends up happening is that you release hydrogen and oxygen gas as a result of basically reducing the water to its elements. So what's going to happen is it is going to fizz quite a bit. It's really critical that you do not seal this, because if you do, it presents a potential explosion risk. So use the long stirrer basically to make sure that this goes in a solution. It actually went in a solution pretty well without me even doing anything. Again, because it's such a small container, the thing that when we think about doing is capping it and shaking it. Please don't do that. Then what you're going to do is just drop her out a little bit, and literally, because the volumes have changed somewhat significantly, you do not need very much of this to demonstrate the result. You're going to take your cup number 11, essentially add whatever number of drops starts to give a color change. In this case, it will probably only be 1 or 2. What's illustrated here is a lot of fizzing, because again, what you're doing is reducing water. But what's happened is the pink has gone to black, essentially because cobalt 2 has been reduced to cobalt 1. What you may not be able to see real obviously, so you'll want to kind of show this to the students, Originally, this is why we had the larger volume, is it would have been more obvious with a bigger thing, but you can tilt it a little bit so that the students can see what's going on. You might start to see a precipitate form. Literally, I only put 2 drops in here, and that was plenty. So you're going to do the same thing with your cup number 12. Probably 1 drop or so. This is a light blue, which is copper 2. And then when we add a drop, it should lighten a little bit. It will tend to go gray first, but you can sort of tell that there's a different, it's more of a yellowish color change. This one's precipitating out because the concentration of the copper is lower than what we originally thought was going to happen, but you can sort of see the yellowish color here. The black is precipitating because there's simply too much reductant here, whereas the cobalt is more of a gray color and it's staying in solution. And so what you're going to want to do ideally is keep these out for the students throughout the rest of your program, and when you have time, if there's a break or something like that, have the students check back in terms of seeing the color change hopefully go back. As the material reoxidizes back to the +2 states, you should start to see it go back to more of an orange color for the cobalt, and the copper may end up going back blue. You'll just have to see what happens. And this also depends on how much sodium borohydride that you added. I think that covers most of it. You are given this additional cup that's labeled 13. If you would like, you can transfer this rather than doing what I did, which is leaving it in the container. If you're more comfortable transferring it to this and then doing the drop ring, you're welcome to do that.
Susan, you might mention that, what does this have to do with metals? Obviously, these are all metal salts, and what you're doing is you're changing the oxidation states using the sodium borohydride. The question we wrestled with a little bit in the committee was, do we get into expressions like oxidation states? Well, it's kind of hard to not do that when that's what's going on in the experiment. One can refer to the fact that we have oxidation reduction going on, and that's the reason for the color change, but we thought it might not be terribly inappropriate to mention to the kids up front what an electron is, and just something as simple as the negative part of an atom, and kind of let it go at that. Because we're going to be talking about electrons, both in terms of reactions and redox reactions and transfer of electrons. We're also going to be talking about electrons when we get into the conductivity experiment. And we're also going to be talking about elements and compounds. All of these kids are going to, when you first start, recommend that you say something about, what do you know about chemistry? Can you name any chemicals? How about what you're breathing? You're breathing oxygen, nitrogen. Those kinds of things are elements. They're not compounded with anything. And mention that in the air, there's also water vapor. There's CO2. Those things are compounds. 2 different elements, or 2 or more elements mixed together, if you would, in a chemical compound. So I don't think it's too inappropriate to use the terms electrons, elements, and compounds. Oxidation states, I don't know. Leave that up to you guys as to whether or not you want to use that phraseology. And one other thing that I think should be mentioned is Susan referred to the fact that it would be great if we had some location toward the center of the room where we would have a demonstrators table. As a matter of fact, on page 11 of the script, it actually recommends that you set up a table somewhere in the middle of the room where the students can actually see the results of these experiments. We're going to do some other things as the morning progresses, that the students need to really be able to see. So if this table were more in the middle, we don't want to screw up John Carroll's arrangement, but in the libraries, if you can set up a table in the middle of the kids, that might not be an inappropriate thing. Anything else on experiment 1, Susan?
Just one last note in terms of disposal. If you're getting rid of this at the end of the day, it's fine for it to go down the drain, but be aware that the borohydrite's going to just keep reacting, and if it's not all consumed before the end of the class period, when you pour it down the drain, it's going to fizz a bunch. So you want to run a bunch of water. The volumes, again, are smaller than we originally designed, but what's going to happen is that you're going to end up pouring a bunch of black junk down a library drain, and there might be some questions about that. So make sure that you rinse sufficiently with additional water. And in this, we can check on these later.
Yeah, we'll
So
come
you
back
can
to
see
them.
the color change.
Another way to dispose of things is down the commode too. A lot of us will take a bucket to the library and at the end of the program, dump a bunch of stuff together into the bucket and then dispose of that into the commode someplace. Works a lot easier sometimes than putting things down the drain. Thank you, Dr. Wang.
Well, so that's doable. I just want to say that if you do that with this stuff, it's going to react in your bucket. So don't be surprised if you compile everything and suddenly it starts fizzing.
It's not going to hurt anything.
No, it shouldn't. But if you're not prepared,
It's not even exothermic, is it?
it'll be, yes, it is.
Not that much though. It's not going to boil over or something.
Yes.
Guess what?
Yeah, I have something
Oh.
for you, not to disrupt the whole.
Yes, ma'am.
I didn't want to do that. All right, as a solution for the fact that we only have 10 mils, and we're putting all of that borohydrite in, putting very concentrated one drop, why don't we ask the demonstrators to put far more water in the cup, put the borohydrite in that, and then you have a diluter solution, and you'll see the color change, but it'll go back faster.
I've already, the issue really was that I had considered that when I weighed out the borohydrite, but I didn't want it to happen to the point where you'd be dripping and not see anything.
Okay.
So I think this is actually really good, it's trying to change color again. And this guy is actually starting to go pink. You can't see it from where you're at, but yeah.
Our next experiment, in the next experiment, we are going to test some of the properties of one of our more common elements, namely iron. What we're going to do is we're going to check several metals in this experiment to see whether or not they are ferromagnetic. We're going to select the only one, which is of the metals that we have, which is iron. We're going to see if an iron nail put into a compass, put into a cork, makes a compass that really works. And since it won't, since it hasn't been magnetized yet, we're going to find out how to do that. All in experiment number 2. For experiment number 2, each student is going to need to go into this packet and take out the black card magnet that's in the back. So if you do that at this point, and one of the things I recommend when you get to the library and the kids start to come in, try to get kids at a table, 5 at a table, as much as possible. Because there are so many experiments that require all 5 kids' participation. If you have onesies and twosies at tables, it's okay, but it probably works better if you have 5 people at a table, okay? So arrange so that way if you would. All right, let's start by going to the center of the table, and there are 5 metal samples that are here. One is a big strip of zirconium. Another one is a little piece of aluminum foil. Another is a copper rod. The fourth is a paper clip. And the fourth or the fifth rather, is a little strip of magnesium, okay? So the magnesium is the tiniest one. What I'd like to do, hopefully having 5 students at each table, each student take one of these and remember which one that you had. If you only have 2 or 3 students at a table, obviously they'll have to double up. But if the students can each take 1 or 2 of these, depending on how many students there are, let's check them with the card magnet to see if any of these things are magnetic. We know the answer, of course, but the kids don't. So the only one that should be even close to being magnetic should be the paper clip. And that sometimes even weakly because it has this kind of zinc coating on it. As a matter of fact, we're going to refer to that as a sample of zinc a little bit later. Now, please don't discard those samples. Keep those metal samples with you and remember which one you had and remember what the metal is. Okay? Next, there is a bowl of water in the middle of each table. I'll bring this over to you guys. And a cork with a finishing nail in it. If one of the students would retrieve the bowl and another take the cork and the nail and float the cork and nail in the water and give it a bit of a spin. And let's see which direction it ends up at. Okay. Over here at this table, which direction did you guys end up with? Pointing this way?
Yes.
Okay. Over here? Pointing almost perpendicular to that. And over here is pointing that way. Pointing toward the blackboard. So we have all kinds of random directions at this point. I've got my trusty cell phone. Dr. Nichols.
Yeah.
I've got my trusty cell phone here. And I'm actually going to take it out and find out where north is. This thing says north is that way. Is the lake that way?
No.
That says, where's north? North is that way? Well, this cell phone doesn't work very well then. Okay. I have no idea what the reason for that is. All right, obviously the cork pointers at this point aren't magnetized and they aren't actually pointing north-south as they would in a regular compass. So each table has a little permanent magnet, and if one of the students would take the cork and take it out of the water and dry it off a little bit, if there's a paper towel handy, it should be, dry it off a little bit with a paper towel. Then hold the cork between 2 of your fingers, even if the other student do this. Hold the cork between 2 of your fingers, take the permanent magnet and run it across the nail in one direction only. Once, twice, 20 times on both sides of the cork. On both sides of the cork. 20 times. It's got to be the little magnet because the card magnet isn't strong enough. Why the world would my compass on my phone not be pointing true north?
I don't know.
Okay, put them back in the water. And now let's see if they all point in the same direction. And we'll see if this ferromagnetic property of iron really works. We can magnetize iron. Let it settle down. Make sure it's in the middle of the bowl, not touching the sides. It should be pointing north-south when it's all said and done. Anybody else have a cell phone that would show north and south? See what you get? Okay, which things are these pointing at? Toward the whiteboard?
It's north. This one's north.
Is it doing it? Yeah, it doesn't want to get hung up on the side. So north is that way?
Bob, we're on the north side of the building.
Okay.
This is the north,
so north
side of the
is
building.
this direction here, right?
North is that way.
North is that way, okay. Well, the neighbor probably doesn't know which is north and which is south.
Well,
It
this
should
one
point
does.
north-south.
Great job.
Is yours doing it?
Yeah.
Good. And this one will too, eventually. So what we've done is we've used the fact that iron is ferromagnetic to actually magnetize a common nail so that it now becomes the pointer of a compass. So that illustrates one of the properties of one of the marvelous metals, namely ferromagnetism. Okay. What's the matter, Helen?
Nothing.
Did it work?
I couldn't get the compass to come out of my phone.
I can't get the compass to work on mine, so we're in the same boat, I guess. Okay. Our next experiment is going to involve thermal conductivity. In the front of each table is a cup with ice water in it. Let's bring that front and center. There's a large piece of aluminum foil with 4 different objects on it. Namely, there's a galvanized, that is zinc nail, a piece of copper rod, an ice cream stick, wooden ice cream stick, and a plastic spoon. What I'd like for you to do is take the aluminum foil, put it over the top of the cup, and mash it down around the edges of the cup. What we're going to do is we're going to pump those 4. One of the students to actually start testing the temperature of the ends of those samples that are sticking out of the foil and see which one is getting cold first and which one is the coldest. Carol, what do you get? Which one got cold first and the coldest? The copper?
Copper. Yeah.
That's about right. In your script, there is a list of thermal conductivities, and copper leads the bunch by no small amount. So the copper should, of course, be the one that gets the coldest the fastest, followed by the zinc, and the nail is basically zinc coated, so that should be second. Then obviously the ice cream stick and the knife, they're not going to do anything in terms of cold transfer. So once again, we run into these little buggers called electrons, and we're actually moving electrons from hot to cold, or cold to hot in this case, and hot to cold, I should say. And that's what is the reason why these things are cooling off. Much the same way that electricity transfers through wires. Much the same kind of thing. Okay, so that...
One thing you haven't mentioned are the words that they're supposed to be writing down on the...
Oh, you're absolutely right. You're absolutely right. Let's go back to the reverse side of that form that each one, or to the top side actually, of this form that each of the students has with them. And let's look at some of the words that are there. There's 6 words.
Which one of those words would you associate with experiment number 1? On the front of the sheet, color. So put number 1 next to the word color. Which one would you associate with experiment number 2? That's the ferromagnetism of iron from which we made a compass. I think compass might do for experiment number 2. For experiment number 3, that's the conduction experiment. Cold was what we transferred. So put number 3 next to the word cold. Okay? We'll complete that as we go. Thank you, Helen, for picking up on that. We'll complete that as we go, and we'll find the magic word at the end. Anybody guess what the magic word is? No, we're not going to go there. Okay. The next experiment, number 4, is kind of an interesting one. I think this is Sharmila's favorite. It's using reactivity to predict where metals are going to be found in nature. And I'm using my sheet, excuse me, my cheat sheet, of course. By the way, I apologize to the audience. I picked up a head cold last weekend. Here it is 1 week later. And I can't tell you how many people I run into that have these stupid colds. And you can't shake the thing. So anyway, do the best we can. All right, the first thing we're going to do with experiment number 4 is we have a group experiment. We have a 10 mil tube with copper sulfate in it. Now, this is something that's on your errata sheet. We are supposed to have put a little bit of salt into that copper sulfate, regular table salt, as we were putting together the materials on GAC day. For some reason, that was neglected. That step was neglected. So we put a packet of salt in with this experiment in all the kits. So if one of the students would pick up the packet of salt, open it up, and open up the 10 mil vial, and put just a little bit, a pinch of salt into that 10 mil vial. Recap it.
You need to wear gloves when you're doing this.
Gloves, yeah. Everybody put on their gloves, please. Did you guys get some salt in there and shake it up good? Okay, now what we're going to do is we're going to, in this experiment, the first part of this experiment, we're going to expose one metal to another. And we're going to find out which of the two metals is most reactive and least reactive. To do this, we've got a piece of aluminum foil there and a long wooden stirrer. So once you've got the salt in the copper sulfate and you've shaken the vial up a bit, take the piece of aluminum foil, sort of curl it up, and put the aluminum foil into the copper sulfate in the 10 mil vial. Once you've got that aluminum foil into the copper sulfate, push it down into the copper sulfate with that long stir that you've got. And we're going to let that sit for a bit. next part of the experiment once you got that done. Ross, on page 29 of the script, go around each table and pour about 30 mils from the 3 vials into each cup of into the 2 ounce cup of fill it about half full. And you have 3 vials to do that with. At this point, we're about ready to start. We'll come back to that experiment. Please set that down. We'll come back to that. At this point, we're going to go to an experiment where we actually test the reactivity of various metals in both water and weak hydrochloric acid. If you have an assistant, now is the time for your assistant to pick up the 3 vials of 0.25 molar HCl that are marked 4 and fill the cups marked 4-2 about halfway. We don't want the students fooling with that HCl, so we ask the assistant, somebody who's an adult, to fill up those cups for us. All right, now we're going to do a quick demonstration. We have some calcium beads, calcium turnings, I guess I should say. And we're going to check them in the presence of water and see what kind of reaction that we get. Now here again, we ask that the demonstrator's table be somewhere in the middle of the room where the students can watch what's going on. So this is going to get interesting. As you know, what happens when you add just a little bit of water to calcium metal. That is calcium, isn't it? Duh. Nothing's happening. It's supposed to be going crazy.
It's fizzing.
It is?
Sure. It's fizzing.
Ah, now it's going. Okay, there we go.
You gotta get the coating off it first.
Ah, it's got a coating on it. Okay, let me take this around and show it to all of the students that are here. Look what's happening with calcium with just some water. Now it's kind of going. And it's exothermic as mad, as you know. Okay?
Didn't melt the cup yet?
Well, we got polypropylene cups so that it wouldn't do that. Okay? So you can see what happens with calcium in water. Now, at the demonstrator's table, you have those same 6. That's just a demonstration. We're not going to let the kids have access to the calcium. Okay?
Just a comment.
Yes, ma'am.
The fumes are a little irritating, so we probably don't want to get too close to the kids.
Okay. The comment was the fumes are pretty bad, so maybe stay in the center of the room at your strategic point, if you would, and let the kids see what's going on from there. We now have the same six samples that each of you have at your tables. And as a demonstrator, if I don't drop the silly things, I'm going to start dropping these in a cup of water that I have at my table to see if any of the other 5 metals that we have, again, they're the same things that you had on your table. I'm going to put the magnesium in first and see if we get any reaction with water. I'm going to put the paper clip in the water. The idea is to see if we have anything else that gives us the same kind of violent reaction with water as the calcium did. Here goes the copper, and here goes the zirconium. Okay, at this point, I don't see anything. Mike, you see anything here?
Well, you guys did the same thing. Okay.
Well, they're students. They're supposed to be doing that.
Students aren't supposed to be doing it yet.
They're in,
The students are putting the metals in the hydrochloric acid already. So go ahead and do it.
This is
No,
acid.
this is, no, that's water.
That's water. That's
Is it
water.
water?
It's water.
Yeah.
41.
41 is water?
Yeah.
Yeah.
Okay, well, get the
Okay.
tweezers now. There's tweezers around here someplace. Right up there, Helen. Fish those samples back out. Okay? And now put them in the cup marked 4-2. And
Oh,
you're
this is
to,
this.
supposed to
This
be
is acid.
observing these now. Anybody see any reactions in the water?
No.
No reactions of those metals in the water. Okay, so now put them in the acid in cup 4-2 using the tweezers. One at a time, yeah. One metal sample at a time. Give it 30 seconds or so to see if you get any reaction with the hydrochloric acid. And what I'd like for you to do is with each sample, remember what they are now, with each sample, see if after 30 seconds you're getting any bubbling, and rate the reaction as per the bubbling that you're getting. Rate that from 1 to 10, with 10 being the most reactive. Which metal is the most reactive? And rate them all from 1 to 10. 0 to 10, actually.
Probably want to have
Put
wear
them in and
gloves.
take them out.
Do what?
Gloves. Gloves.
Everybody has to wear gloves, absolutely. Sorry about that. I'm supposed to have...
Well, but you said that earlier.
Yeah,
Yes, thank you very much, Susan.
I
yeah.
mean, you never put gloves on the first time he told you to put gloves on.
See there, Shamila.
Demonstrator. That was the demonstrator.
No, as soon as we.
Everybody's supposed to have gloves
It
on,
said the gloves.
Gloves and masks.
and what?
including all the PhD chemists. They're all supposed to have gloves on too.
I have a question.
Yes, ma'am.
I should know this. Is the total volume of HCl 30 mils?
Per cup,
But how much is in the vials?
150.
What
30
happens-
times 5 is 150.
Okay, so it's,
You fill those cups up, whatever it
We would
says, about a
have
half
5
full,
of them.
whatever it is,
okay,
and you'll find that it works.
okay.
Are you getting any bubbling at all from any of the samples?
Yes.
Okay, rate them from 1 to 10. 0 to 10, I beg your pardon. With 10, the calcium that you saw was a 10. Okay? Because it was reacting in just water. Rate these samples 0 to 10. This is only 0.25 molar HCl. I was admonished not to go any stronger in HCl with the kids, so 0.25 will have to do it. Okay, let's take a look at the back of the, is that where it is? Yeah, the back of this sheet that has the word puzzle on the front. Let's turn it over and go to the results section where it says reactivity results. Okay? Now you will have rated each one of those metal samples. And actually in the script, by the way, what it says to do is to have each one of the students take the tweezers and put a sample in the HCl one at a time. Okay? Observe the sample to see how much bubbling you get, and then go to the second student, and so forth. Okay? Okay, how are you guys doing over here? You got all the samples in there? Okay, one more. Okay, give you about 30 seconds to observe the reactions that you're getting.
This is number 1 again.
This is the aluminum foil and the copper sulfate.
Copper sulfate after we.
After, I don't know,
It's a
20
tie.
minutes or something like that.
the results of that experiment. The first, the metals are all listed alphabetically on the back of the crossword puzzle sheet. First metal listed is aluminum. What kind of result did you get with aluminum? 0 to 10. Hello? Anybody? Did you get any reaction at all from aluminum? Well, you guys have got the answers, of course. Cheaters. You're supposed to be using the back of the crossword or the word puzzle form, okay? Trust me, the kids won't have the script, okay?
We hope.
All right. So, realistically, what did you see with aluminum?
Not much.
Should be about a 0. Not much reaction at all. The calcium we saw with the water was 10. Okay? Copper. 3, 2. What'd you guys get over here? 0? Maybe a 1 for the copper. How about the magnesium? Pardon me?
Yes.
A lot? What number did you give the magnesium? 6? Okay, magnesium is 6. How about the zinc? Anybody on the zinc?
And the zinc was the paper clip.
Yeah, zinc was paper. Anything from the zinc?
1.
1? All right. And the last one is the zirconium. Anything at all from the zirconium?
It's way too big. But what does this say significant?
Okay. Based on those numbers, the zirconium should be about a 0, 2. Based on those numbers, on the right-hand column where it says metals in order of reactivity, list the metals from most reactive to least reactive. Obviously, you start with calcium. What comes next? Magnesium. After that? Hello. What's after that? Copper, zinc. Yeah, I think those were pretty low. Aluminum, maybe. This should be the third one. And then copper, zinc, are tied, and zirconium comes in last. Okay, so the metals that are least reactive. Sharilla, you want to talk about that business? The reactivity of metals and whether or not metals that are more reactive or less reactive are found, how they're found in nature?
I'm not sure what I can say that.
Well, obviously metals
She's probably better too.
metals that are the most reactive. Who? Lois.
Probably better, yeah.
Nah, we're not going to pan it off on Lois. The metals that are most reactive are obviously reactive. So they're going to be found more often than not as ores and compounds in nature. The metals that are the least reactive is the reverse. Metals that are least reactive should be found more in their elemental state more often than not. Let's go back to the first part of this experiment where we put the aluminum foil in the copper sulfate. Now, when it comes to aluminum and copper, which is the most reactive according to the results we just got? Which is more reactive, aluminum or copper? Aluminum, right. Aluminum is more reactive. What we did with this reaction is we used a synthesized copper ore, if you would. We used copper sulfate, which started with synthesizes an ore, which is the reverse of the way copper should be found normally in nature. And we used aluminum metal, which is also the reverse of how it should be formed in nature, found in nature. What happened? Hello, anything happened with that experiment?
I got copper.
Yeah, the copper came out of solution, which indicates that the aluminum is the most reactive. and the copper is least reactive, and it reverted back to its elemental form. Okay? So that shows a little bit of how reactivity of metals can give an indication of where we expect metals to be found in nature. Right, all you chemists? Is that right?
It's a single displacement reaction in
There you go.
general chemistry.
There you go. There you go. And there's double replacement reactions too. Okay. So much for experiment number 4. Experiment number 5 is a rather interesting experiment. We're going to use metals to enhance metals. And what I like to do is I like to do part number 3 first. You've got at your table, in the middle of the table, 3 cups. One with a blue solution in it, one marked 53H, and one either blank or 53W. There's also 2 nails there. Mike, if you would zero in on those 2 nails for a second. One of the nails is what's called a bright finish nail. It's relatively pristine. The other nail was an anodized nail that I treated overnight. It is important that the demonstrators look at items to do the night before the demonstration on page 5 of the script. In the materials that you got, there are materials for a so-called Experiment 0. In Experiment 0's materials is a 50 ml vial with vinegar and 5 anodized nails. All you have to do for prep overnight is to put those 5 anodized nails, the ones that come in Experiment 0's materials, into the vinegar vial overnight in an attempt to remove the zinc anodized coating. Okay? Do not cap that vial overnight. There is hydrogen evolution. Okay? In the morning, in the materials with Experiment 0, there's a couple more things. There's a pair of plastic gloves, and there is a piece of sandpaper. In the morning, pour the vinegar out of the vial, rinse the nails off without touching them yet, put on the gloves that are there, take a piece of a paper towel, which was supposed to have been included. I'm not sure it's there, but if not, take a paper towel, get a couple double thickness paper towel, lie it down on the table, lay the nails out on that paper towel, take a second double layer paper towel, and rub the zinc coating off. It's probably oxidized zinc at this point from being in the vinegar. Rub it off onto the paper towel.
This is already done, right?
It's done for today, yes. For the kits, when you take your kit home, this has not been done.
Right.
You have to do it the night before the experiment. In the morning of the experiment, take the nails out, lay them down on that on a double paper towel, and then with your gloves on, rub as much of the zinc oxide coating off of those 5 nails as you can. It's messy. Expect there to be a lot of zinc oxide dust. Okay? Don't get it on your hands. Wear those gloves. When you're done and you've got as much of the zinc oxide off as you can get off, then take the little piece of sandpaper that's there and roughen up the surface of those nails to try to get any excess zinc off of the nails. So, pardon me? This is what you have right now, those 2 nails. The one nail should be shiny, it looks like it's been treated and scratched and so forth. The idea, yes, the idea is to expose the iron in one nail. We could not find uncoated nails. The idea is to have just an iron, plain iron nail, hopefully, and a galvanized nail, which is the second nail. Now, there is a paper towel there and 2 packets of salt. One of the students should now take those 2 nails, put them in a cup of water. Put those 2 nails in a cup of water. Another student open the 2 packages of salt and pour them onto the paper towel. What we want to do is create a very corrosive environment. So what we're going to do is we're going to take the wet nails out of the water one by one and rub them into the salt, roll them into the salt to try to get a salt coating on the nail one by one, and then put them in the peroxide. Once you have a salt coating on them, put them in the peroxide. One by one. Okay, where are you?
Peroxide.
Does it say age?
It says H.
Yeah.
Go into the cup of water.
What all we're going to do is wet the nail so the salt will stick to it.
And then fall
Okay.
off when it goes into the
And
peroxide.
roll them in the salt to get salt on the nails. And then put that salty nails, if you would, into the cup marked 53H and let it sit.
What's going on?
All right. While that's cooking, that is, I'm doing this out of order.
It's not
gang,
really
okay?
cooking. Just
That's actually
It's
the
bubbling.
third part of this experiment.
little.
But I want to give those nails a chance. Well, I want to give the peroxide and the salt a chance to work on those nails while we do the rest of the experiment. Another one of the experiments, since we're now dealing with coating metals with other metals, in our case, we're now going to coat a relatively cheap metal, namely copper, with an expensive metal, namely silver. Electroless plating of copper from silver nitrate, okay? This demonstrates to the students that there are a lot of cases, like in the world of jewelry and others, in which a very relatively inexpensive base metal has an expensive topical metal, if you would, put onto it. So we're going to take the aluminum foil, we're going to put it into the silver nitrate, and we're going to let it sit there. Now this is just a demonstration. You have the materials for just one of these on the demonstrator's table. Okay? Now while that's going on, we're going to go to part 2. And with part 2, we're also going to coat a metal onto a metal. You have at each table a 50 ml vial marked V, a nail, 5 pennies, a paper towel, a pipette, and a package of salt. If you could pull all those things forward, what we're going to attempt to do in this experiment is to coat copper onto a nail. The nail that's there. That nail happens to be a bright finish nail that has a zinc coating on it. We're going to start by opening the vial marked V, as in Victor. There are 5 pennies there. Now, the 5 pennies tend to be dirty pennies. The dirt is not dirt, quote unquote, dirt. It's copper oxide, copper 2 oxide. And what we're going to do is we're going to attempt to clean these pennies with the vinegar solution, just the vinegar right now, to see if we can remove some of the copper 2 oxide. In so doing, the copper 2 ions will go into the solution and turn the vinegar blue. Now, I gotta tell you, it takes probably more time than we have for this to happen, but we're gonna give it a try. So slide the 5 pennies one by one into the vinegar. Cap it up and swirl it around and see if anything's happening. Give it 30 seconds, 30 seconds to a minute. I can tell you not too much is going to happen. The salt is a bit of a catalyst in this case. So now open the packet of salt, pour all the salt from the packet into the vial. Swirl it around to dissolve the salt. And again, we'll give it about 30 seconds to a minute to see if anything happens with those pennies. Each student is supposed to have this at their table, by the way, at their place.
Definitely cleaner.
Okay, in this short period of time, are the pennies cleaning any?
Yes.
Yep.
Okay. Is solution turning blue at all?
Nope.
Well, one issue that we have is we didn't get white vinegar with this experiment. So it kind of tends to cloud the solution a little bit. I picked up a box of vinegar. We picked up a box of 6 jugs of vinegar, not realizing it wasn't white vinegar. But it's no big deal. All right. If we waited long enough, that copper oxide would all come off, or most of it would, and it would turn that solution a light blue. And then we could use those copper 2 ions in solution to coat the nail. But since we don't have forever, there is a cup of copper sulfate. For the kids, there's a cup of blue liquid in the middle of the table. And each student has a pipette, I hope. So if the first student would take the pipette, get a pipette full of copper sulfate, squeeze it hard and get it full, and squirt it into the vial. Take the cap off and squirt it into the vial. And pass the cup down to the other students. Once you've got your copper sulfate, pass the cup of copper sulfate down to the other students. Once everybody has got their copper sulfate into the vial rather, what we're going to do is each student is going to open the vial back up again. Once it's all mixed up, well and good. And now take the nail at your place and gently slide the nail into the vial. You can leave the cap off at this point and we'll see what happens. Okay. Those were parts 1 and 2 of this experiment where we're coating one metal with another. Now we're going to come back to that in just a second. But in the meantime, let's go to the 2 nails that were put in the one that's at your table. There's only one left. All right, now let's go back to the cup that's marked 53H with the 2 nails in them. Is anything happening? Students?
Yes.
Very good, students. And what is happening? The nail that had the coating removed is
Bubbling.
bubbling. What else?
Rusting.
Rusting. Key word. The nail that was untouched, the bright finish nail, is what's happening to it? Anything happening to the anodized nail?
It's not.
A lot or a little?
It's rusty.
But just at the tip.
Right. The point of all of this is that we're talking about coatings of one metal protecting another metal. We didn't actually put a coating on the nail. It was already there. But we did remove it and then test a nail with the coating removed to see if the coating did in fact protect the nail that wasn't, whose finish wasn't removed. Is that what we're seeing? Is the nail with the finish removed rusting and the other nail pretty much not rusting?
Mm-hmm.
So I think we can make the point that here in Ohio, in particular, with all the salt that we spread around, if we didn't have anodized metals used in cars, like the anodized coating that's on the nail, we have a lot more rusting going on than we do. And that's apparently the secret to cars not rusting these days. Let's go back to the vial with the nail in it. What's happening to the nail?
Getting a brown coating.
It's getting
Brownish.
a brown coating, and that brown probably is copper. So that's another way of coating one metal with another. We started, where's the silver nitrate? What do we do with that? Here it is. We started over here putting copper into silver nitrate. And can I borrow somebody's tweezers? You don't have it. This is a demonstration. But again, you need to be somewhere in the center of the students so that all the students can see what's going on. I'm going to reach in there and pull that out. Oops, and we have a nice, well, we had a nice silver coating. Thank you, sir. Nice silver coating on the copper, and for everybody to see, and there's also some silver at the bottom of the vial. Okay? Alrighty. Any comments on this so far? Sorry about that. Bring it over to you guys. Any comments, anybody, on anything so far? Yeah, third graders. Come on. There it is. Okay. Lastly, we have an experiment that's a little ill-fated. It's with memory wire. We ordered the memory wire from the same source that we ordered it from several years ago when we did this, and we got shorted a little bit. But there's at least one piece of memory wire at each table, Lois? Okay, there's at least one piece, so it's going to kind of turn into something of a demonstration. Do we have some hot water ready, Lois?
Oh, I see it.
Where's the hot water, Lois? No, there's no hot water in my furnace. Oh, there is now. Okay. Lois is on the ball. Here's what I've been looking for. No wonder I lost it. Okay, I'm gonna. If you have an assistant, this is a great thing, of course, for the assistant to do. There's a paper clip at your place, should be someplace, along with the memory wire. And what I'd like for you to do, one of the students, is to take the paper clip and straighten it out. And then take your pencil and wrap maybe a third of the paper clip around the pencil. Curl it up around the end of the pencil. What kind of temperature do we have? temperature we have now? Yeah. And then take the piece of memory wire and do the same thing. Curl the end of it around the pencil. Good, that's great. Now what we like to do is take those two pieces of metal, the paper clip with the curl on the end, and the memory wire with the curl on the end, and watching closely, put the two wires into the hot water with the curl end down. And what happens?
Goes straight.
Somebody's gone straight around here.
Yep.
Did you put it in? Okay. Does it want a curl?
No, it doesn't.
Give it a real tight curl around the end. There you go.
Just bend it in half.
Okay. Everybody see the memory wire went
Bend it
straight?
in half.
You can't get our memory wire.
Memory wire isn't curling well.
You don't need too much of a curl, just enough to demonstrate the point. To make the point.
There.
You guys getting it to work over there?
You broke it.
Mark, you guys getting it to work?
Mm-hmm.
Great. Okay. The only thing you can tell the kids
You
about
broke the
this
memory wire.
experiment is that the paper clip's a thumb wire,
It's
if you
already
would,
cold.
You put it not.
and the memory wire is a smart wire. And the best analogy you can give, I guess, is that all the kids will know that there are several forms of water, two of them being regular water, liquid water, and ice. We call those different phases. In the memory wire, believe it or not, there's two different phases as well. One is that they're both solid phases, though, two different phases. And the phases are temperature dependent. As we go from one temperature to another, you go from one phase to another, and that's the reason why the memory wire straightens out. So you can do that at home, and we're actually going to let the kids take several of these things home. They can take their cork and their magnet and card home with them. They can take that memory wire home with them. And I think that's about it. We don't want them to... Ceramic. Not ceramic. No. The little round magnet stays. Yeah. There's in the back of the script, it tells you which things can be taken home and which can't be taken home and what stays and what goes. Okay, any comments on the whole thing? Oh, that! I keep forgetting about that silly thing. Let's go back to this thing. Where did we leave off? 3, okay. Experiment 4 was about using reactivity to predict where metals are in nature. And what we did was we poured water and acid onto metals, and what happened when we did? Gas evolved. So you might say that number 4 goes next to gas.
It's twofold.
4-1. 4-1.
No, 4-2 is gas.
4-2 is gas, I beg your pardon. 4-1 is the two forms of metal. One of them is ores that we talked about. Okay? By the way, it's all on your cheat sheet. I should be looking at my cheat sheet. Experiment number 5, enhancing metals with metals. What did we do in several of the cases? We plated metals, so plating is number 5. And then number 6, the memory wire, obviously the thing there is memory. So if you would fill in the crossword puzzle based on those results, you'll get the magic word, which is maybe even plural. Okay?
Can you zoom in on the color change thing from the beginning?
Yeah, you want to demonstrate some more, Sue?
Well, not necessarily. I mean,
Point
you
out
can-
what's happening?
You can sort of see the blue, but there's too much. And you can see the pink too.
Which is which now,
It's
Susan?
back. Copper's gone back to blue, but it's precipitating out. And the cobalt is going back to pink.
So those are experiment number 1. The script mentions that they could revert to original colors, and that's what's happening.
Yay.
Okay, comments. Thank you very much for attending today's program, and thank you to John Carroll for hosting the program. Thank you, Dr. Nichols, for being our cameraman, and thank you, Mark, for all of your goodwill and your help getting all the program together. Thank you. We're done, Mike. All right. Bye. Okay, what do you guys think? Third graders? Yeah, what do you third graders think? Was there enough wow?
Cut that part out.
Yeah, here's some of these.